All right, so let's do a few complex computations to get a sense for really what this complex number stuff is all about. So let's say we'll start with x to the fourth equals minus 1. So x squared equals minus 1 led to needing I and minus I. Does x to the fourth equal to minus 1 lead to anything new that we need to add? This is getting to the sense of, are we done yet, right? So for example, with x to the fourth equals 9, that's the fourth root of 9, which you have to kind of add in if all you've done is add in the square roots, right? You need all these other powers. Now with the real numbers, we just kind of found a way to do it all at once. All of them are in there. So we didn't have to concern ourselves, but if we were doing it one kind of thing at a time, we could keep adding these things to the system. Is I like that or not? You know, with the real numbers, it was like this, we're filling in all the gaps, and then everything was filled. Here, it's like we gave one solution to one problem. Well, I guess two solutions. I and minus I. Did that somehow magically do everything? Well, yes. Yes, it did. Not going to tell you quite now why that is true. Called the fundamental theorem of algebra. It's a nice theorem. That's another. It's for another time. Anyway, x to the fourth equals minus 1. What happens? So, well, this is x squared equals minus 1. And what's the square roots of minus 1? It's plus or minus I. So x squared should be equal to plus or minus I. All right. So let's just look at x squared equals I. And so we want x equals the square root of I. So what is the square root of I? That's a good question. Seems like we might need something new for that. It's the square root of minus 1, right? What is that? Here's where the magic happens. So what's a complex number? It's v plus iw. That's supposed to be equal to the square root of I, right? So its square is supposed to be equal to I. Or you can do minus I. We'll do I. So square it out. V squared minus w squared plus 2ivw equals I. So real parts and imaginary parts kind of are separate components. So and v and w are real. That's our assumption here. Without making that assumption, you don't get much of anything. So v squared minus w squared equals 0, 2vw equals 1. Can we solve these? Yes. Yes, we can. We can solve in two ways. One is equation v squared equals w squared means that v is equal to plus or minus w. And so you get 2 v squared equals 1, maybe with some plus or minuses or whatever, but because v is supposed to be positive, real, this you can't take the negative of square root, so we'll just go with the positive here, and so v is equal to plus or minus 1 over root 2. And essentially you get 1 over root 2 minus plus or minus 1 over root 2 plus or minus when you plug in everything and everything that could work, whatever, It's like that. Now, in the coordinate plane, that's these 4 points. And when you raise it to the 4th power, you get -1. There's 4 of them, and they all work. All right, good. The other approach would have been you get v, say, equal to 1 over 2w. You get v squared, oops, sorry, 1 over 4w squared minus w squared equals 0. Multiply out away that fraction, and you get 1 minus 4w to the 4th equals 0, or w to the 4th equals 1/4, w equals 1 over root 2, and then v equals 1/2 over root 2, but that's just 1 over root 2. The magic of square roots. Square root of 2 divides into 2, giving you square root of 2. Good. All right. So again, and of course these are all plus or minus, whatever. Okay, good. So that's that. So what's the square root of I? Square root of I is equal to, let's say, 1 over root 2 plus I 1 over root 2. And you can get other square roots of i's by doing this, I guess, anyway, this might be a good time to go to our good friend GeoGebra. And so, what can GeoGebra do for us? Well, let me put in the point 1 divided by the square root of 2 1 divided by the square root of 2, like so. Let me zoom in. Okay. And you know what I'm just going to do? I'm going to pop in a circle with radius 1. Okay. So we're on this unit circle. Circle of radius 1 centered at the origin. Now, I created a little tool called multiply, 2 complex numbers. Basically, oh, shoot, okay. Maybe I can, A. Okay, so I multiplied A by itself in this way. The formula for this is just, doing that square for that multiplication. So you multiply them and you get the product of the 2 real parts minus the product of the 2 complex parts. That's for the x component. And then the y component is the product of the x and y's of the different points. Anyway, so that was a squared. And then what I can do is multiply a to that again, so that's a cubed. Oops. Oh, interesting. Somehow I ended up with point there. So that's a cubed. And then I get to a to the fourth. Oops, 1d. There we go. And there you go. It's at minus 1, 0. All right. And if you wanted to try the other ones, so let's say minus 1. So that's on the other side. What happens? So first, a squared goes to minus I. And then a cubed goes over to that first point we had, and then a to the fourth goes to minus 1, right? And then we can go here and do minus minus, so that's starting in the third quadrant, going around, goes up to plus I, and then, so that's a squared, and then a cubed goes all the way around to the fourth quadrant version, and then a to the fourth is, again, minus 1. And then the last one to try out is the one that starts in the fourth quadrant. There we go. A squared is this point C, and that's minus I. A cubed goes here, and then a to the fourth. So it's like we're wrapping almost all the way around, except missing just that one little quarter bit, right? So like this portion of the circle is just being subtracted from A each time. So that multiplication goes, just like we were adding it in the other direction. So that's the magic and mystery of complex multiplication. So yes, so those are the 4 solutions. All right. What's next? Well, so we did x to the fourth equals minus 1. What about something slightly simpler? X to the fourth equals 1. How does that go? Well, we know that x equals 1 works. And we know that x equals minus 1 works. What about anything else? Well, I squared equals minus 1, and minus 1 squared equals 1, so I squared squared equals 1. And I squared squared is just I to the fourth, right? Powers multiply like that. Power outside works the same. So I to the fourth is a solution, and if I is a solution, then minus I is the solution. Okay, great. So now we have 4 solutions for x to the fourth equals 1. Who knew that the fourth power of 1 had so many options? Well, 4, right? So, what can we do with this? Well, one thing you can do is x to the fourth minus 1 is going to equal to the factors like so. So anything that you plug in, get 0 for this thing. So 1 minus 1, I minus I, that's a factor in this polynomial. Like so. And if you multiply these out, then, it's just like these boxes, right? So let's say xi and x minus I. You get x squared minus ix plus ix and minus 1. And so that's equal to x squared minus, that's 0, and then minus 1, right? So this becomes x squared minus 1. Wait, what? Sorry, it's a plus 1, plus 1, plus 1. And then you have these other 2 factors. And this is like the real factored form of x to the fourth minus 1. We'll talk more about that, but factors are nice. And so this is how things go. Now, roots, I should say complex roots of real polynomials. We'll talk about polynomials more in depth soon, but they're basically just powers of x with coefficients multiplying those powers of x and adding them up, and the powers are all natural numbers. So nice, easy stuff in terms of what we could envision still, but more complicated than lines and quadratics. It's like the next step. They have a lot of rich structure and behavior. In many ways, polynomials you can use to approximate quite a large, wide array of phenomena, particularly stuff based in reality, because they're, well, in reality we never get to infinity, and most other things have issues with that. But anyway, so complex roots, a real polynomial. So these are things that when you plug it into this polynomial thing, you get 0, like minus I or plus I in this example. Complex roots of real polynomials come in conjugate pairs. This is probably the most important thing. To know about them. So that, what does conjugate pairs means? It means if v plus iw is a solution, then v minus iw. These are conjugate pairs. So it's plus the imaginary thing and minus the imaginary thing. You have them together, and so that when you multiply them together, the imaginary stuff vanishes. So that v plus iw, v minus iw, that becomes v squared. Let's see, I guess the i's become plus w squared, and that's it. All right, so the coefficient over here was 1, and well, w was 1, basically. And so 1 squared and 1 squared, and that's what you get. Anyway, so you can see this with the quadratic formula. So the quadratic formula was given a quadratic ax squared plus bx plus c equals 0. You get minus b plus or minus the square root of b squared minus 4ac over 2a, right? There's that plus minus. Now, where did complex numbers come from? Well, or come into this? Well, if b squared minus 4ac is less than 0, then this becomes minus b plus or minus I square root of 4ac minus b squared over 2a. So you pull out a minus 1 out of the square root. That introduces the I. You get 4ac minus b squared. You get the plus or minus I. Now, this all hopefully should make some sense that you need both the plus and minus version of I, because we could have picked I to be the other one, right? There's just 2 square roots of minus 1, and there's no way to distinguish them, right? We just gave one a name, and then the other one's the minus 1, minus of that. There's no way to sort of say, this is the one we want. So if I is a solution to something, then minus I is. Now this is only for the reals, right? Once you start having, if you had polynomials with complex coefficients, then I is already kind of known. That's kind of built in. You would have a preference already built in, and then this whole argument kind of fails. But here, if everything is real, A, B, and C, and so forth, then this is what the result is, and that's the thing. Okay, so that's the quadratic formula. Let's do an example of this. So let's say x squared minus 4x plus 20. Why not? It is what it is. It won't be nice, but I don't care. So a equals 1, b equals minus 4, and c equals 20, right? And so the quadratic formula would say you've got 4 plus or minus the square root of 16 minus 80. You know what? I guess maybe I do care. So what do I need? If I wanted so if I wanted this to be maybe it's plus 8. 2. Let's do plus 8 here. So this is 8, and so then I think this minus 32 over 2. There we go. Will become 4 plus or minus the square root of minus 16 over 2. And so that's 4 plus or minus I times 4 over 2, or 2 plus or minus I, 2I. 2I. Okay. So that's nice. And so what this also means is that you can check this. So this is a way of actually checking that this thing works out if you want to do the multiplication. I'm not going to do the multiplication. But you have these two forms. So you plug in the roots here, is x minus whatever the root is, right? And so 2 plus 2i and 2 minus 2i. So if I've done all this correctly, this should multiply out to the original polynomial. All right. Now, what I want to show you, we'll go back to, well, first of all, let's do Wolfram alpha. So x squared, that one squared, minus 4x plus 8 equals 0. Let's see what the good old Wolfram alpha gives us. So that definitely looks like there's no real solutions, right? And then here's some alternate forms. Here's the complex solutions, 2 minus 2i and 2 plus 2i. Here they are in the complex plane, and tells you a lot. And what happened if I just wrote in that polynomial quadratic? Would it give me that factored form? Yes, see? Here you go. X minus the two roots, right? I guess you actually get a little bit better information if you don't set equal to 0. Okay. Oh, and that's the, here's the vertex form. So that means the vertex is at 2, 4. All right. So let me do a new GeoGebra. And set up that navigation bar. Oops. Oh, sorry. Okay, we got the input bar. And all right, so we have GeoGebra. What am I going to do? I'm going to graph this polynomial. Plus 8. All right. So that's the polynomial. You can see there's no real solutions. And you say, okay, well, this isn't going to help me find the complex roots, right? Like, this is all real stuff. Well, there's a little trick. So, so the vertex form was, x minus 2 squared plus 4, right? So get rid of that original one, and it's just the same one, right? Good. So here's the trick. Take that vertex form and negate that squared term. So that's flipping the parabola around the horizontal line going through the vertex. So that's reflecting it. So what was going up is now going down. Same vertex, right? So same vertex. Here, I'll line it up here. Go up like this, and go down like this. And same shape. Okay. And now, let's see. Oh, let me see. What do I want to do? I want to get these roots, and then I want to get the midpoint here, and then I want to do a circle through the point. And there we go. With me so far? Now I'm gonna sorry, x equals x of c, like so. So that's the line going through, vertical line going through the center, and now there we go. So D and E, what are they? 2, 2, and 2 minus 2. Now if we're suddenly thinking in the complex plane, that's our solution. 2 plus 2i and 2 minus 2i. So this is a way of actually getting the solution, complex solution, using just graphical techniques. So you reflect the parabola, look at the roots that way, find the midpoint. That's just going to be the vertex there. And then draw a circle that fits in there. Pretty nice, huh? Alrighty. And yeah, if we were to let's say we were to change that to 3, and then change this to 3, and then everything changes, and it looks like the complex solutions would be 2, 1.15, and 2 and minus 1.5. So that's for the quadratic 3x minus 2 squared plus 4. 3x minus 2 squared. 3x minus 2 squared plus 4. Let's see what Wolfram Alpha does for us here. Again, this graph here, it's no real solutions. And here's the exact ones, this picture, and if we do approximate form, 1.15, right? So, hey, it works. And you can do that with any parabola. Basically, that's it. So, even for complex roots, you don't need to do the algebra if you've got something like GeoGebra or what have you. You need to be able to draw the parabolas and circles. What was key to it was the vertex form, being able to flip that. So you just negate the square part involving the x after you do the completing the square. Alrighty, and of course you can complete the square using the vertex. So if you got the graphical methods, you get the vertex and whatever. Okay, so hopefully that's a taste of complex numbers. Just to recap, I squared is minus 1. That's the definition of I. Minus I squared is also 1. Minus 1. You create these complex numbers by real number plus real number times I, and those two things kind of like live in almost like separate realities. So it's like a coordinate pair. We can view that in the complex plane. You can plot them. There's a lot to do with angles in terms of these things and the magnitudes. So actually I should probably show that. Let's go back here. If we just delete this, that should... Okay, so we, to show what I mean, yeah, let's take a circle with center, the origin, radius 1, like so. Put on 2 points on the unit circle, and then we multiply them. Like so. B, C, that's not right. That's weird. Why is it doing that? Huh? Huh. Weird. Okay, I'm just going to do it out. X of B times X of C minus Y of B, Y of C. x of b times y of c plus x of c times y of b. There we go. That's the right picture. And now, oh, I guess I also need a point 1, 0. All right, so now I can do this angle. These two angles. Do, 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 do. So here are the angles of all of them. It's a little clearer. It's going to be a bit more clear if I pull these over to the first coordinate. All right, let's see. So alpha is the angle from EA to B, so that's 14.5 degrees, and beta is 34.87 degrees. And then their multiplication is 49.39. You add these together, 35 plus 14 is 49, roughly. And so it goes. And so as I change C, notice that D is changing just by that same angle. And if I change B, it's also changing by that. We're adding up these angles between them. So we need to have two complex points on a unit circle, so a circle of radius 1. When you multiply them, all you're doing is adding the angles. So that's a nice little geometrical thing going on there. And then if you have it off the unit circle, so this thing, D is now got the same sort of magnitude as B. And if I detach both of these points from these objects, basically, so here's C at 1/2 and B at 1. D is is that making sense to me? All right. So like 2.12. Segment going here. So let's move this. So if C was actually at 1/2 and B was at 2, right? It'd be 1. Then if I rotate it roughly in the same magnitude, D goes along with that. But as I extend it out, it's just scaled. So like 3/2 times 1/2 is 0.75. And they're at roughly 90-degree angle. And then, so essentially, when you multiply two complex numbers, you kind of, the relevant things are how far away they are from the origin. That's what we call the magnitude. So if one is 2 units away and another one is 3 units away. Then when you multiply them together, that point will be 6 units away from the origin. And then you have to locate around sort of a circle of that size where it is. So that's where the angles come from. So then you figure out the angle. So if one was at 30 degrees and the other one was at 40 degrees, then their multiplication is at 70 degrees. The angles add. So complex numbers have some very rich and interesting geometry going on with them. They just do. And they have interesting properties of intersecting with stuff that seems just kind of like based on the real numbers, but things happen on the real numbers sometimes that only kind of makes sense if you look at the complex plane. So that's kind of the natural home for where our numbers ultimately sit. And so sometimes you have to go to the complex plane to really get a good perspective of what's driving that. And yeah, those are the complex numbers. I hope this makes some sense. Unfortunately, there isn't really too many interesting problems without going into more depth of things. I mean, you can play around with what we've done and everything in terms of the algebra and stuff of just multiplying these things together, having the polynomials and roots and stuff, but then it's not really all that. It's practicing for using them in some other context, which probably won't be for some time. So, but at least at the very least, you can think of, okay, complex numbers, it's like this plane. The y-axis is the imaginary numbers, x-axis is the real numbers. We get imaginary numbers coming from the square roots of negative numbers. Quadratic formula is really where stuff happens. And there's some cool geometry related to it. Hopefully you can take that away from all of this.